In this video, we're going to talk about the four main separation techniques that we use in this class. These separation techniques are all going to be physical changes. They're not going to be chemical reactions. This is basically what you do when you want to try to isolate the results of a chemical reaction and separate the things that you made, because you very often make more than one product, and then you end up needing to use some of these techniques to separate those products from each other. And that's typically how most chemical reactions happen. So distillation, what is it? Well, it separates two different liquids based off their different boiling points. Now, distillation is most commonly used in the production of alcohol. Basically, you ferment alcohol the same way someone would make wine or beer, and this is your mixture of alcohol and water, right? That's typically what you have as a result. There's usually other things, but we're going to overly simplify this. The problem, or the good part, is alcohol boils at like 70 something degrees Celsius and water boils at 100. So what you end up doing is, if you heat this water up to, let's say, 77, which I believe is the boiling point of alcohol, the alcohol will boil and the water won't. So now that steam will make its way up this tube. It'll hit the thermometer and read 77. The thermometer is really there so that you know that if you know the temperature of the things that are boiling, then you can figure out which ones are coming off based off their boiling temperature. So for example, if this thing read 100, then I'd know I'm boiling water off. But if this read 77 and I know that alcohol boils at 77, then I know I'm boiling the alcohol and that the water is staying behind. Now, the problem is, once you turn it into a steam, you then put it into this pipe, which is called a condenser. Now, what this condenser does is literally its name. It condenses a gas back into a liquid. And the way it does that is basically the bathroom mirror effect. So you know when you take a shower, you see all the fog that collects on the bathroom mirror? The reason that is because the steam given off by the shower is in the gas phase, and when those steam molecules touch the glass, it's much colder, it lowers their temperature, and then they condense back into a liquid, and that's where you see all that stuff building up on your mirror. That's essentially what's happening here, but very fast. And so the hot steam, or the hot alcohol, will hit this condenser, and it will get cold. If you notice, there's a water in and a water out. I'm not mixing it with water. The tube goes straight through, and the steam is allowed to go straight through. But as the steam is going through, it hits the walls and then turns into a liquid. And then eventually they all kind of collect and form droplets, and then those droplets kind of all build up, and once you get enough of them, they come out this way. Having the water go in and out is just there so that I can continue to keep this glass nice and cold, because if I didn't have the water, this would happen, the condensation would happen initially, but then it would warm the glass up. And if it warms the glass up, then there's no point, it won't condense any further. So the in and out for the water is just to continually refresh the temperature of this tube to keep it as cold as possible all the time. And then what will drip out of here? Well, you would get pure alcohol that would drip out of here if you were at 77, and then if you were at 100, you could get pure water. It really depends on what temperature you're at and what you have mixed in this mixture. But you get one thing out, and it depends on its boiling point. So that's distillation. I will show you one of these in class, but we typically don't do these. These tend to be a little bit more dangerous, and the glassware is expensive and easily broken, so we don't have a lot of these. Chromatography. Chromatography separates substances based on their ability to stick to each other, or in this case, their ability to dissolve in water. I guess it depends on how you word it. But basically, here's what you do. Now you probably have seen this in biology. In biology, you usually, depending on your teacher, you'll take a dry erase marker, or some teachers will have you do a chlorophyll extraction from a plant leaf, and you'll put a little bit of green stuff right there at the bottom, and then you'll put some water in here right up to the bottom, and you're basically letting the water get wicked up or sucked up through the paper, just like a paper towel would do when you put it on water. You've all seen that. That's essentially what chromatography is. The only difference is I have a little spot here that has multiple compounds in it, and those different compounds like to dissolve in water, some more than others. The ones that really like to dissolve in water well, they're going to move the most with the water because they like to be in the water the best. And the ones that don't like to dissolve in water, well, if they didn't dissolve in water at all, then they won't budge. That's like trying to, if you try to clean off nail polish or a Sharpie marker using water, it's not going to work because the material doesn't dissolve in water. You have to use acetone or alcohol in order to dissolve it, because that material doesn't likes to dissolve in those rather than water. And so what I'm doing is I'm separating things out. Now, why is this technique still used today? It's just a piece of paper and a piece of glass. It's really a convenient, fast, and keyword, cheap way of identifying materials. The reason it's used is simple. You have what scientists will typically do is they'll take a spot, they'll put a spot down that they know what the chemicals are, and then they'll test versus other spots that they don't know, and they just do a comparison technique. So if I know that this spot, for example, is compound A, and then I run it against my unknown, if there's a spot in the same location, then I would say, all right, well then compound A must be in this unknown mixture. And then the same would be true for compound B, and then the same would be true for compound C. So it's really just a comparative tool to identify what chemical you're dealing with. So if you didn't know which one you were dealing with, you would, take a bunch of samples of known chemicals that could potentially be what you want, and then you would compare what you had to those, and then the ones that raise up to the same level are most likely the same thing. Now, why do we do this? Again, it's cheap. This filter paper, you can buy, hundreds of feet of it for a couple bucks. It only takes water and a glass tubing, and so this is a really easy, quick, and cheap tool to use. There are tools that would give you definitive answers, but those that equipment, like for example high pressure liquid chromatography and things like that, they're very expensive to run and operate. And so until you absolutely need a 100% definitive answer, you use the chromatography paper. And even in professional labs they'll do this, because running it the other way, the more expensive machines, might be $100 every time you try to run a sample through, whereas chromatography, you can do it for pennies. And so they'll do it this way until they absolutely have to pay for the expensive equipment to do it. So that's chromatography. Filtration, this one is an easy one. Anyone who's made coffee has done this. Filtration separates solids from liquids. Keep in mind, if the solid happens to be dissolved in the water, then it will not get caught by the filter. It'll pass straight through. So an example, if I had a solution of water and coffee grinds, let's say I used boiling water, and rather than filter it, I just dumped the coffee grinds directly into my water. If I then slurry them all up and pour them through a coffee filter after the fact, it's a little messy to do it this way, but I mean, it could be done. The filter will stop the solids, the coffee grinds themselves, because they don't dissolve in water. And then any of the caffeine and flavoring that did dissolve in the water that makes the coffee that dark color, that would go through. So keep in mind, dissolved solids will pass right through. Solids that don't dissolve, they get caught by the filter. So when I filter my coffee water here, I'm not going to get pure water and then just coffee. I'm going to get what we call coffee, and then the grinds, the things that can't dissolve, will stay in the filter. So that could be used to separate sand from water. That's a very common one. If you have sandy water, like let's say you were, in a survival situation and you needed to filter that water, all you need is a piece of filter paper, or in this case you could use a piece of clothing or a cloth or anything like that, and you can filter out the sand and the grit. And now keep in mind, there's a limit to filters, meaning filters are rated to on how small of a particle they can filter out. So, whereas a coffee grind's an easy one, a bacteria might be very hard to get out. And so it depends on the filter size. But in general, filters separate solids from liquids. Evaporation and boiling, we'll go over these last two. This is a pretty common one. So evaporation is the conversion of a liquid to a gas below its boiling point. Notice, keyword here, below its boiling point. In other words, when a liquid is evaporating, it's not creating those classic bubbles that you see when you boil water. So evaporation is the same process as boiling. The difference is evaporation happens below the boiling point, so we don't see those bubbles, and it takes a really, really long time. Whereas boiling can take minutes or maybe hours at most, but boiling will be much, much faster because you're adding heat, which is forcing the liquid to turn into a gas directly. The evaporation happens more naturally. Later on in the year, we can come back and use a theory called the collision theory to explain exactly what causes evaporation if it's below the boiling point, meaning why are the water molecules able to get into the air if they don't have enough temperature or energy needed to form a gas directly. Classic examples of this, this happens all the time. This is how we make sea salt. So if you get that, if you go to the store and you buy that fancy salt, like the pink Himalayan sea salt or something like that, they don't all have to be pink. They are typically made by taking ocean water and evaporating the water or boiling the water away, depending on what you want to do. Evaporation is slow but cheap because you don't have to use energy to do it, and boiling is fast but expensive, so it depends on what you want. But that's typically how we make salt. That's also, if you remember in history, I don't know what history class you would learn this in, but Gandhi did the Salt March, where he went to the ocean and they took ocean water and they boiled it away, and what was left was the salt. So this is something that people have been doing for a very long time, and all it takes is ocean water to do it, but that is evaporation. So that concludes the 4 techniques that we use to separate liquids in this class. You will definitely be using 2, possibly 3 of them throughout the year in the labs that we do to separate different chemical compounds from each other.